should know for computer science using logic. All right, so you've seen this already, but it's no harm in either this will help you remember universal Turing machines, or this will help you remember first order logic, right? Either way, it's good to do. All right, so here, computational P sorting is the computational problem sorting. I sorting is a list of numbers that you want to sort, right? And what does PI represent? It represents the required answer. And what's the required answer? Is if you take a list of numbers, then the required answer is you sort those numbers, right? Everybody get the notation that we're doing here? All right, so why is P sorting sort of computable? Well, it's computable because there exists an algorithm, merge sort. There exists one sorting algorithm, merge sort, that no matter what the input is, it solves the problem, right? Everybody get that? That's what we've been doing over and over again. All right, so the game is I come up with the algorithm, the adversary comes up with the input, and then the algorithm, of course, when the adversary knows what the algorithm is, so it comes up with the worst case and a bigger, right? The input is going to be bigger and scarier than the algorithm, right? And then we have to prove that the algorithm works on this input. Is everybody with me here? All right. That was just another warm-up to make sure we knew what we were talking about. Now, what is the universal Turing machine? This is a universal computational problem, right? This is P stands for computational problem, and instead of it being the sorting problem, it's the universal problem. All right? And what is I universal? It's an input to the problem, right? And instead of it being a list of numbers, the input has the description of a Turing machine, and it has an input to that Turing machine, right? That's the input to the universal Turing machine, to the universal problem, right? Everybody follow that? And what is the required output? Well, the universal computational problem, given an input, of course, the input is a Turing machine and an input, is to tell me what that Turing machine will do on that input, right? Everybody understand this computational problem? I give you an M and I give you an I, and you interpret M as a Turing machine, and you tell me what M does on I as a Turing machine, right? Everybody get that? All right. So now, why is it computable? It's computable because there exists a thing, there exists a Turing machine that solves the problem, right? We can name one Turing machine, call it M universal. It's a Turing machine, right? Such that, right here, the universal Turing machine is a Turing machine that is given the description of a Turing machine as input, and it simulates that computation, right? So we construct the universal Turing machine. Then the adversary looks at our universal Turing machine and gives us a worst case input. What's the input? Is some M and some I. And one thing we'll note is, suppose that our universal Turing machine had 1,000 states, right? We have to build this universal Turing machine, and we build it with 1,000 states. Well, this M over here that the adversary is giving us, it's going to have 1 billion states, right? If our universal Turing machine had 1 billion states, then the adversary would give me a Turing machine with 1 billion states, right? Because the adversary, when it comes up with its M and its I, it knows your universal Turing machine. So it's going to make its M and I bigger and scarier than your universal Turing machine, right? Does that make sense? And then we have to prove that this universal Turing machine will properly interpret M and I and simulate M on I and tell you what M does on I. Right? Everybody following this?